Inverses of functions. So inverses are things that undo each other. We know a few of these already. Addition and subtraction, so addition undoes subtraction and vice versa. And multiplication and division. So multiplication undoes division, and the same goes for division undoing multiplication. Functions also have inverses. So to find the inverse of a function, you're going to do a few things. First of all, if we have it in function notation, we're going to replace f of x with, well, y. Then switch the placements of the x and y variables and resolve it for y. The way we denote an inverse is we use f to the negative 1 of x. Now, this negative 1 is not actually an exponent. This is just denoting that our new function is the inverse of the original. So let's find the inverse of 2x plus 3 algebraically. So first thing is we're going to replace this f of x with y. Then we're going to switch the placements of our x and y variable. So instead of y equals, it's going to be x equals 2y plus 3. Then we're going to resolve this for y, so that means moving the 3 to the left. So I get x minus 3 equals 2y, and then dividing by 2. So we have y equals x minus 3 over 2. Now, to denote that this new function is the inverse of the old one, we're going to replace this new y with f to the negative 1 of x equals x minus 3 over 2. So the inverse of my original function is x minus 3 over 2. Now, some properties of inverses. So because the inverse functions interchange the input and the output, since we flip-flopped x and y, that means the domain and the range are also interchanged. So if we look at the tables of our new functions, so we have the blue table and the red table. The blue table is the original, the red table is the inverse. So if we look for my domain, my x's, negative 2, negative 1, 0, 1, 2, well, that is now my range of my new one. Same thing for the range of the original. This negative 1, the range, negative 1, 1, 3, 5, 7, is now the domain of the inverse. Everything about this is backwards. They use the exact same numbers, they're just flipped. The last thing is inverse functions are a reflection across the line y equals x. So again, the blue is the original, the red is the inverse. So if you notice, if you try to connect a line from point to point, it's exactly perpendicular to this y equals x line. This is a reflection across y equals x. That's true for every inverse function. It's a reflection across y equals x. So let's try example 1. Consider the function f of x equals 2x to the third plus 1. Find f negative 1 of x. So remember, this f negative 1 of x, this is talking about the inverse. So that means I need to find the inverse of my original f of x. So step 1 is change the f of x to a y. So I have y equals 2x to the third plus 1. Then step 2 says interchange the x and the y places. So we're going to have x equals 2y to the third plus 1. Wherever y is, put an x. Wherever x is, put a y. And then we're going to resolve this for y. So I need to get rid of the add and subtract. So I have x minus 1 equals 2y to the third. Divide out the coefficient. So then I have y to the third equals x minus 1 over 2. Then I need to get rid of my third exponent, which means I need to take both sides and cube root it. That's how we get rid of an exponent. So we have y equals the cube root of x minus 1 over 2. The last thing is we need to make sure we're using the correct notation. So this new y is actually f negative 1 of x equals the cube root of x minus 1 over 2. So this is the inverse of the original function 2x to the third plus 1. Example 2. Consider the function f of x equals 2 square root of x minus 3. Find the inverse. So again, change the f of x to a y. Y equals 2 times square root of x minus 3. Then we're going to interchange the x and the y's placements. So I have x equals 2 square root of y minus 3. And then we start solving. I need to resolve it for y. So divide both sides by 2. Square root y minus 3 equals x over 2. Then I need to square both sides to get rid of the square root. So I end up with y minus 3 equals x over 2 squared, plus 3 to both sides. So we have y equals x over 2 squared plus 3. And then last, make sure we denote this correctly. So this y is actually f to the negative 1 of x equals x over 2 squared plus 3. Final part of inverses, proving if two functions are inverses of each other. So the definition of an inverse is this: if and only if f of g of x is equal to x and g of f of x is also equal to x, then that means f of x and g of x are inverses. So here's what this means in English. Basically, find the composition f of g of x, remember order does matter, and g of f of x. If both results are x, then yes, f and g are inverses. If one of them is not equal to x, then it's already messed up. These are not inverses of each other. So example 1. Determine whether the f of x equals 3x minus 1 and g of x equals x plus 1 over 3 are inverses. So the first thing we need to find is f of g of x. So this is that composition of functions. So we're going to take g of x and plug it into f. So we have y equals, remember this is f, so we're going to take 3 times. Now the x is actually the g of x function, x plus 1 over 3 minus 1. And then we're going to simplify and hopefully we get an x out of this. So first let's multiply. Remember this is 3 over 1. So what we really have is 3 times x plus 1 all over 3 minus 1. Anything over itself is a 1, so we're going to just ignore that. So this ends up with x plus 1 minus 1. And then combine like terms, 1 minus 1 is equal to a 0, so we're just left with x. So far I have the result I want. Now we have to also make sure the opposite is also equal to x. So the second thing we need to figure out is I need to do g of f of x. I need to do both. Now this is backwards, so now we're going to take f of x and plug it into the function g. So g of x is a fraction. Now this says x plus 1, so the x is actually f 3x minus 1 plus 1 all over 3. So since there's no number in front of the parentheses here, that means we're going to drop the parentheses, 3x minus 1 plus 1 all over 3. We'll simplify the numerator. Negative 1 plus 1 makes 0. So we have 3x over 3. And 3 over 3 is a 1, so all we're left with is x. So because both results were in x, that means yes, f and g are inverses. Ta-da! Okay, example 2. Determine whether f of x equals 8x to the third and the cube root of 2x are inverse functions. So again, we're going to start with f of g of x. We're going to take g of x and replace it inside the f function. So my f of x is 8x to the third. So y equals 8 times whatever x is, and x is now this g function here, the cube root of 2x to the third. And now we're going to simplify. So a cube root and a third power are inverses, so that means these cube roots and this third power undo each other. So this is really 8 times 2x. Well, 8 times 2x is 16x. Well, according to our rule here, it says that both results have to equal x. Well, f of g of x did not equal an x. So that means automatically that no, these are not inverses. I don't even need to figure out the other composition. They both need to be x, and since the first one was not y equals x, then we're done already. It doesn't matter what g of f of x comes out to be. Example 3. Determine whether the functions x plus 5 and x minus 5 are inverses of each other. So 1, f of g of x. So we're going to replace g of x inside f. So g is the x minus 5 and f is the x plus 5. So the f function, we're going to start here. I have x, and x is really this x minus 5 plus 5, and we're going to simplify. So there's no number in the front of the parentheses, so this is really x minus 5 plus 5. Negative 5 plus a 5 makes 0, so we have y equals x. So far, we have what we want. Step 2 is I need g of f of x. So we're going to go backwards. We're going to take f of x and place it inside of g. So g is y equals, here's the g, x, which in this case is the f function. Again, there's no number in front of the parentheses, so we can ignore them. X plus 5 minus 5. Positive 5, negative 5 make a 0. We have y equals x again. Both results in y equals x, so that means yes, these are inverses.